Hi, everyone. So welcome to the quantum session. Our first speaker will be Jane, who will be talking about learning quantum channels.
Hello. Okay, mic is working. This is predicting quantum channels over general product distributions. This is joint work with all of these wonderful people. If you have technical questions, I'll probably redirect it to them because I don't really do quantum and they do. So the objective, the task at hand, is to predict the behavior of an unknown quantum channel. So you've got some state, and you're going to run it through some process in the lab and then measure it with respect to some known observable, and you want to predict what happens if you do this. All three of these objects are represented as 2 to the n by 2 to the n Hermitian matrices. So actually, really what we're trying to do is learn this function, trace of OE rho. Previous work establishes that this task is actually equivalent to predicting the expectation value of an unknown observable rather than putting this unknown channel in the middle. So from here out, I'm going to talk about it as if it's just this task, predicting trace of O rho. And also, we're in an average case distributional setting, so we want to learn over some distribution, which we will assume to be a product distribution, d tensor n, over states, which must also be product states. We want to learn a hypothesis H that is close to trace of O rho in expected squared value over states drawn from D. And our access model is that we can prepare a state rho and put it through the channel and measure it. So this is basically a membership query type of model. And we can also sample classical descriptions of the states drawn from the distribution. So in general, this problem is hard. There are product distributions for which it's hard. In particular, you can encode the uniform distribution on the Boolean cube, and then the task is equivalent to learning an arbitrary Boolean function over the uniform distribution, which requires exponentially many queries. But this isn't really a quantum distribution, so is learning easier if D is guaranteed to be truly quantum? So we'll formalize what truly quantum means. So we'll represent D as a distribution over the block sphere. All single qubit states can be represented as three-dimensional unit vectors indexed by the standard Pauli matrices, and D is going to be a distribution over these unit vectors. So let S be the second moment matrix of D, indexed by the Pauli matrices. If the operator norm of S is 1, then D encodes a classical distribution. The one that we just talked about on the previous slide is an example of this. And all other second moment matrices with operator norm 1 are just some rotation of this distribution. So we'll call D a truly quantum distribution if the operator norm is smaller than 1 minus eta. Intuitively, this is a distribution that is spread out within the block sphere, rather than just being supported on two opposite points. So the main result is this. If D is a 1 minus eta truly quantum distribution, then there's an algorithm with time and query complexity poly n. Think of epsilon and eta as constants, so this is poly n, that outputs a hypothesis that's epsilon close to trace of O rho over D. We're building on previous work of Huang, Chen, and Preskel, who give a result that requires a pretty strong distributional assumption, which they call local flatness. In this work, we are going to use a distribution-specific basis for truncating, and this allows us to generalize the set of distributions that we learn over, though it's only really qualitatively weaker, not strictly weaker because there are locally flat distributions that are not product, but we still consider this a more general class of distributions. So to show you how this works, I'll give some classical intuition. This is basically a classical special case where the distribution is classical but satisfies the formal definition of being truly quantum. So D is a distribution over this shrunken interval, minus 1 minus eta. That parentheses should, that's a typo. The minus sign's outside the parentheses, whatever. Minus 1 minus eta to 1 minus eta, and F is a bounded multilinear function. So think of it like the multilinear extension of a Boolean function. Then F is epsilon close to a constant degree polynomial. We're going to show this. This is actually so simple we can prove it in this talk. and it should give some intuition for why the quantum result holds. So we can express f in the biased Fourier basis using the mean mu, which is the mean of d. But we should also consider this other basis, which is the orthonormal basis for functions over d. And it's almost the same, except this xi minus mu, instead of being over square root of 1 minus mu squared, it's over sigma, which is the standard deviation of d. So this is just a rescaling of the biased Fourier basis. It's just that since the distribution d has smaller variance than the biased Bernoulli, that's like what the biased Fourier basis is for, it's rescaled by this factor of sigma over square root of 1 minus mu squared. And when you have s-wise products, the scaling factor is raised to a power of s. So we want to show that the low degree part of f is epsilon close to f. Therefore, we want to show that the high degree part of f has mass epsilon, so expected squared value at most epsilon. So we should just expand it in our standard biased basis, which we showed on the first slide. That phi is the standard biased Fourier basis element. And then rewrite it in the orthonormal basis for d by pulling out the scaling factor. By Parseval's theorem, this expected squared value of fd is the sum over the degree at least d Fourier coefficients squared. Then just pull out the factor of the scaling factor raised to the power of d, I mean it's squared, so 2d, since the size of s is always at least d. And then you have this extra term, which is the sum of the original Fourier coefficients squared, which is at most 1 by Parseval's theorem again, and the assumption that f is bounded. So basically, we end up with that the scaling factor raised to the power of 2d is a bound on the expected squared value of f if all of the terms have degree at least d. This scaling factor is always at most 1 minus eta by the assumption that d has been shrunk into this interval 1 minus eta. And so that gives us this exponential decay with d. So this allows us to conclude a classical special case of our main theorem, that if d is this 1 minus eta concentrated classical distribution, then there's a polytime algorithm that learns any bounded multilinear function over d. And outputs a hypothesis that's epsilon close. So to make this a quantum result instead of a classical one, we need to make a few changes. So Huang Chen Preskel contains a proof that truncation in the standard Pauli basis works when d has mean 0. The standard Pauli basis is a basis for Hermitian matrices for 1 qubit, and then that, if you tensor it to n, that gives you a basis for Hermitian matrices for n qubit observables. So we define a biased version of this basis, which looks a lot like the biased Fourier basis. And the proof that we have exponential decay with d, it's not exactly the same, but it is basically similar. And here's a note on how the learning algorithm is actually implemented, because we don't actually know d. We don't know what the basis functions are. But we actually don't need to. We can just draw samples from d. Recall that the access model says that we can draw samples in the form of classical descriptions. So these descriptions are of the form like a list of trace of p row for each 1 qubit Pauli element p. And for each sample, prepare copies of the state that matches that classical description, and use those to make the membership queries to estimate trace of O row. You make this set of labeled examples and then just run linear regression. You never need to know what the proper basis was. We also give some lower bounds. So like one of the things we're interested in is how much you can generalize the distribution. So we were assuming product distributions, and we think that the set of distributions that this type of strategy should work on is more general than that, but it's not fully general. So we show that there exists a distribution over the shrunken interval to the n, such that any algorithm that learns arbitrary functions over d has to make 2 to the omega of n queries. And what this distribution is, it's very far from a product distribution. It's a code over the Boolean cube. So think of like a code on the vertices of the Boolean cube and then just shrink them all in by a factor of 1 minus eta. This distribution is hard to learn over. And we also showed that the distribution-specific basis is actually important, that if you try to truncate in a distribution-oblivious basis, the analysis will not work. So we give a product distribution over the shrunken interval and a function f, such that if you want to achieve even constant error and you're truncating in the standard monomial basis, so like the standard Fourier basis, then you have to truncate at degree at least omega of n, and therefore take exponential time. This distribution is just a single point, basically, and f is the Boolean majority function. So to wrap up, I'll just kind of zoom out a bit, give the bigger picture. So as of this work, the family of distributions under which all observables are efficiently learnable now includes locally flat distributions, which is what was given in previous work, and now also truly quantum product distributions, which we give in this work. We think it should be possible to generalize this further. What about an n over k-wise product of distributions over k-qubit systems? And what about distributions where, anti-correlated marginals, that's not really the right way to say it, distributions where the distributions over individual qubits are not independent, but they are anti-correlated. These are both things that intuitively should be learnable with respect to, and we have some classical evidence of this. Another question is whether the sample and query complexity can be improved just by better analysis or better use of membership queries, since our algorithm pretty much just uses the queries as random examples. And then finally, are there other applications for quantum analysis of Boolean functions, or particularly the biased Pauli basis? And that's it.
Is there a reason that the bias Pauli basis? Is there a reason that your bias Pauli basis only shifts the Z Pauli Z?
Yeah. So, I mean, the reason we did that is because it makes the analysis easier, but it is without loss of generality. You can take the eigendecomposition of the mean state and take whatever unitary that is and just transform all of x, y, and z by that first so that the mean becomes diagonal. And once the mean is diagonal, then we can use it this way.
Any other questions? Okay, if not, let's thank Jane again. The next speaker is Chi Shun, who will be talking about learning quantum states.
Hello. Hello. Good afternoon. I'm Qisheng Wang, and my topic is improved sample upper and lower bounds for trace estimation of quantum state powers. Shortly, it's improved estimation of trace row to the Q. This work was done jointly with my wonderful co-author, Ke-An Chen from the University of Pennsylvania. Okay, so the problem is to estimate the trace row to the Q, and this is related to the Tallis entropy and the Renyi entropy. And which has the limiting case von Neumann entropy. So the question is, how many samples of row are needed to estimate trace row to the Q? If we can do this, then we can estimate the Tallis entropy and can be used to lower bound the von Neumann entropy and can help analyze properties of turbulent flows when Q is a fractional number. The story begins 2 decades ago, and they first consider the case for Q equals 2, and now known as the purity estimation trace row square. And we know that this can be done with sample complexity 1 over epsilon square by the swap test. And we also know that this bond is tight. And how about the case for the integer case? Generally, Q is greater than or equal to 3. And this can be also done by the generalized swap test, and the sample complexity is 1 over epsilon square. Okay, now how about the non-integer case? The estimation of trace rho to the Q generally can be done with sample complexity polynomial in the rank R and 1 over epsilon, and by a lot of work. And especially for Q greater than 1, this can be done with sample complexity polynomial in epsilon, 1 over epsilon to the 3 plus 2 over Q minus 1, as long as Q is a constant. So this is the summary of the development of this problem, and the last line is our contribution. Especially we show for the two cases. The first case is the case for Q greater than or equal to 2, and the second case is Q between 1 and 2. And especially for the case Q greater than or equal to 2, we show an almost optimal upper and lower bonds 1 over epsilon square, improving the prior work. The way we achieve this for the upper bonds is by noting that trace rho to the Q is unitarily invariant. And we know that for unitarily invariant properties, there's a canonical tester performing weak shear sampling on n copies of rho. So if we can do this, we can estimate the eigenvalues of, also known as empirical sorted spectrum of rho, hat alpha 1, hat alpha 2, blah, 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 hat alpha d. And a straightforward way to estimate trace rho to the Q is to estimate this value. The summation from j to 1, from 1 to d, hat alpha j to the Q. However, directly using this formula and current error bonds will introduce an unexpected dependence on R, the rank, or D, the dimension. To overcome this issue, we instead consider a type of non-plug-in estimator of the form. And this is written as hat P equals to the summation over J from 1 to M and hat alpha J to the Q. The difference is that here M is a truncation and can be much less than D, and the precision of the estimation of alpha J is to be determined. To achieve this, we used a useful tool called quantum spectrum estimation with entry-wise bonds. This is to estimate the eigenvalue of rho with 1 over epsilon square samples of rho, and for each index, the eigenvalue can be approximated good enough. With this, we can estimate the two cases by setting epsilon prime and delta prime and M properly. Then we can show that for the case of Q greater than 2, this can be done with sample complexity almost 1 over epsilon square. And we can also similarly show that the case of Q between 1 and 2 with good choice of M, and we omitted the details of the analysis here. Also, for the lower bounds, we first show that a lower bound 1 over epsilon square for general Q greater than 1. This can be done by a simple problem of distinguishing the two quantum states, like this, roughly 2/3 0 plus 1/3 1. And we can verify that the difference is big enough. It's theta epsilon, and by the Hellstrom Hall-level bond, you can distinguish them. Requires sample complexity omega 1 over epsilon square. And also, for the lower bonds, especially for Q between 1 and 2, we also show a slightly improved bond in terms of Q and epsilon together by the Schur-Weyl distribution. That is, we consider the problem of given row tensor n and determine which is the case. The first case is a random row with eigenvalue r 1/rth and the rest are zeros. And the second case is the maximally mixed state. And we can also verify that the two cases have a big difference epsilon. On the other hand, the success probability can be bounded by the Hellstrom Hall-level bond. And note that for this, the expectation of the two tensor products of row 1 and row 2 is equal to the total variation distance between two Schur-Weyl distributions. And here SWND is obtained by n samples of the d-dimensional maximally mixed states. And note that the Schur-Weyl distribution is closely related to the Plancherel distribution by the inequality. And then we can show the bond by the bounding the success probability. Okay, so we show that for Q greater than 2, the sample complexity of estimating trace row to the Q is 1 over epsilon square, which is optimal up to polylogarithmic factors. And the second case is for the case of Q between 1 and 2, and there is only room for a quadratic speedup. And technically, our approach is based on the Wick-Schur sampling by a non-plug-in estimator, and the prior approach is based on the quantum singular value transformation and the samplizer. There are some open questions. Can we remove the logarithmic factors from the sample complexity obtained in this work? And can we improve the upper and lower bound for Q between 1 and 2? And also, can we find more optimal estimators based on Wick-Schur sampling? And can we obtain optimal estimators for trace row to the Q with restricted measurements? For example, recent work, they show that d to the 3 minus 2 over Q samples are sufficient with single copy measurements. And also, the sample complexity of estimating trace row to the Q for Q greater than or equal to 2 are known to be 1 over epsilon square tight, but only the case of Q equals 2 is known to be BQP hard. So an interesting question is, can we show the BQP hardness of estimating trace row to the Q for general Q greater than 2? That's it. Thanks a lot for your attention.
Are there any questions for Tisha?
Wondering if you can provide some intuition about the difference between the Q less than 2 regime, the 1 to 2 regime, and the Q greater than 2 regime. Like, is there some intuition you can provide about how these problem flavors are different? Or?
Do you mean the sample upper bound? Or?
Yeah, for one of them you got a 1 over epsilon square, and the other was
the other was
suboptimal.
depends on Q.
Right. So, is there some intuition you can provide about why the flavor of these two problems looks
For Q very close to 1, the problem can be ill, and for Q equal to 1, the problem is because the Tallis, this is closely related to the Tallis entropy, and when Q equal 1, it is von Neumann entropy. And in this case, it is known that estimating the von Neumann entropy is computationally hard, and that's the reason I think when Q very close to 1, the complexity can be much higher and should be dependent on the dimension. Thanks.
Let's thank Kishan again. The next speaker is Sean, who will be talking about learning quantum Hamiltonians.
What did I do? Oh. Okay, great. Sorry. Hi, everyone. So today I'll talk about improved algorithms for learning quantum Hamiltonians via flat polynomials. So before I begin, I have a bit of a confession, which is that I don't really know much about quantum learning. So in fact, the real reason, the real technical stuff in this paper is all about polynomial approximations. So for those of you who actually know quantum, I apologize if I say anything incorrect. I hope I don't. But I'll focus the first half of this talk on basics of quantum, especially for everybody who doesn't know, because I certainly didn't. And then I'll discuss the polynomial approximations. So let's first begin with what is a quantum Hamiltonian. So a quantum Hamiltonian is basically a way of measuring the energy of a system. So if you have an n particle quantum system, the Hamiltonian is some 2 to the n by 2 to the n dimensional matrix. And we primarily focus on Hamiltonians based on what's called the Ising model, or like lattice models. So the idea is that if you have a pair of particles, say I and j, that are connected by an edge in this graph, then they have some interaction, which we call h sub ij. And h sub ij is going to be some 2 to the n by 2 to the n matrix that represents the interaction. And then the overall Hamiltonian is going to be some sum of the individual Hamiltonians scaled by some lambda factors, which are some real values. And what actually the HIJs are, not so important. Just know that they have some very simple representation. So it's basically some linear combination of a bunch of large matrices, but they have simple representations. So in this talk, we're primarily interested in learning quantum Hamiltonians. In order to do that, we need to have this thing called a Gibbs state. So the Gibbs state is kind of a way of measuring what the system is doing at thermal equilibrium. And it's basically this: you take this Hamiltonian matrix H, you take e to the power of negative beta times H, and you normalize it to have trace 1. And for those of you who are unfamiliar with beta, beta is this thing called inverse temperature parameter. You can think of it as there is some temperature of the system, and beta is just 1 over the temperature. And then from this thermal equilibrium, you can generate a single measurement of the system. It's kind of like you have this quantum system and you do like a collapse or something like this. And for those of you who don't know anything about quantum, I think a way that I think about it, which I think is slightly incorrect, but it's kind of like you have some complicated distribution and you get a single measurement or a single sample from the distribution. So that's maybe like the oversimplified version of what a sample from this Gibbs state is. So in this talk, we're primarily interested in the question of learning the Hamiltonian from copies of the Gibbs state. So let's say you have a bunch of copies of the Gibbs state. Each one you get a single measurement. And then the goal is to learn this Hamiltonian. In this talk, we assume that the graph is known. So what this means is we know which pairs of vertices or which pairs of particles interact with each other. But we do not know the lambda ij's, which are the scalars that represent sort of the strengths of the interaction. So the question is just learn the lambda ij's up to some error epsilon. And our goal, as is common in learning theory, is minimize the number of samples, which for us is the number of Gibbs state copies, and the amount of runtime it takes. So I'll discuss a little bit about motivation. This is kind of stuff that I've heard. I don't really know much about it. But the point is, apparently, this question of learning quantum Hamiltonians is closely related to some natural classical questions like learning exponential families and learning graphical models. And apparently, it's also related to the mean field theory of spin glasses. There's also apparently other applications that practitioners may care about, like superconductivity, validating quantum devices, and other stuff. So now I want to discuss, here's some pictures of superconductivity in quantum devices. So anyway, I want to discuss a little bit about prior work. So there's been some previous work from a theoretical lens studying both sample complexity and runtime. And the main prior work that I'm familiar with is this work of Bakshi et al., which was able to show that there exists an algorithm for trying to learn this quantum Hamiltonian that for any fixed choice of beta, which is this inverse temperature, it depends only polynomially on the number of particles n and on the error epsilon that we want. And the problem, however, is that while it's polynomial for a fixed beta, it's doubly exponential in beta. So the natural open question that they ask is, well, can we do only singly exponential in beta? And in fact, this is the best we can hope for because there's a known lower bound. So in this work, we exactly resolve that by showing that we can replace the e to the o of beta with something like beta squared. So the previous work, before I discuss our result, I want to discuss a little bit about the previous work. And I also promised that this talk was really about polynomial approximations. This is sort of where it ties in. So the idea behind this previous work is they consider this Gibbs state, which is e to the negative beta times the Hamiltonian, what's really like up to some normalization. But the idea is let's try to approximate this as some polynomial of h. And then what they do is, after you approximate it as a polynomial, they use this crazy machinery of convex relaxation, sum of squares, other fancy stuff. But the main question is, well, if you ignore all this sum of squares and the fact that matrices don't commute as nicely as stuff, it turns out they're able to sort of reduce it to this following question, which is how well can we just approximate e to the negative x, which is this like e to the beta h, as a polynomial in x? And here we're just talking about the univariate linear case, so no matrices. So specifically, here's the main polynomial approximation question. So if we have any fixed epsilon and beta, so epsilon, remember, was the error, beta was this temperature parameter, we want to construct a polynomial q of x that has as low degree d as possible with the following two guarantees. The first is what we call the exponential approximation, which means that q of x should be a very good approximation of e to the negative x, at least between 0 and 1. And the second guarantee is what we call flatness, which basically says for any x that is positive, q of x should be at most e to the power of x divided by beta. So it's kind of like instead of growing like the regular e to the x function, it has to grow a lot slower on the positive direction. But in the negative direction, it's allowed to grow as quickly as e to the x. And maybe the intuition for why this is reasonable is that if we're looking at e to the negative x, well, it could decay forever. But really, it's a polynomial, so it's a polynomial approximation, so eventually it'll sort of grow back up. We just want to say that, at least in the direction where it should be decaying, it doesn't grow too quickly. So this previous work was able to show that if we have such a construction, you can get a sample complexity and runtime that depends as e to the o of d. There's some caveats that have to do with sum of squares, but let's just ignore those. So what they are able to show in this previous work is a polynomial that has degree roughly e to the power of beta. So the overall runtime is going to be doubly exponential in beta. And in our work, we get a polynomial of degree beta squared. So overall, it'll be like 1 over epsilon to the power of beta squared. And so this is, what I said in words. So the natural question is, okay, why not just use the naive Taylor series? I said we're just trying to approximate e to the negative x. Well, we have this Taylor series that works like this and just truncate it. Well, the problem with this is if you truncate at some degree, say s, what's going to happen is while it is a good approximation between 0 and 1, there's this worst case thing that will happen when x is positive s. Actually, this first term will sort of dominate. And as a result, this polynomial will sort of look more like e to the power of s, when really we wanted it to be something like e to the power of s over beta. So I've just drawn this sort of example at x equals 10 for the degree 10 approximation. It blows up really quickly at roughly x equals 10. So we want much slower growth, at least for positive x. So our intuition is based on the way that we construct a better polynomial is we leverage some insights from this special polynomial that exists, which has the following guarantee. So for any degree k and any error epsilon, there exists a degree roughly square root of k log 1 over epsilon polynomial that approximates x to the power of k up to error epsilon for any x less than 1. So in other words, it's a degree like square root of k polynomial, but it's a really good estimate of x to the k. So I've just drawn an example for degree 6 approximating x to the 10. And the way that this is constructed is based on some linear combination of these Chebyshev polynomials. So now how do we actually leverage this? We're going to do the following, which is we're going to write e to the x as e to the negative x over k to the power of k. And then we'll actually, this outer thing to the power of k, we'll replace that with that degree squared of k polynomial I told you about. And then now we're just going to apply the Taylor series on the inside. So we'll get p sub k, which is degree squared of k polynomial, of a degree s Taylor series. And the idea is, well, the worst case we discussed before was when the value, so in this case, x over k is something like s. So when x is equal to s times k, the inside will be like e to the s. And then if you just raise that to the power of k, you would again get e to the s times k. However, in our case, what happens is, well, p sub k, it was actually degree squared of k. And while it's a good approximation of x to the k between -1 and 1, beyond 1, it actually behaves more like exponential, raising it to the square root of k power. So overall, you get something like e to the s root k. So it's like e to the x divided by square root of k. So that's how we get this better polynomial, and then we can apply it to the quantum result that I mentioned at the beginning. So at the end, we'll get something like beta squared log squared 1 over epsilon if you do the math correctly. I said it was actually beta squared log 1 over epsilon. There's some extra extra tweaks that we have to do. So this polynomial doesn't exactly work, but it almost works. So that's all I have. So thank you so much for your attention.
Do we have any questions for Sean?
Yes, Alex.
So what goes wrong if you just directly do a Chebyshev expansion of e to the negative x, or do some other orthogonal polynomials with some other measure?
You're saying if you do a Chebyshev polynomial with each of these things?
No, just directly on e to the minus x. Instead of doing a Taylor series, you just look at some other decomposition of e to the minus
Chebyshev
x.
series.
Yeah.
It's a good question. So this actually it's possible that this works, but there's also so there is actually a version of this that you can do that sort of you take the Taylor series, you shift it by a little bit, and then you do a Chebyshev decomposition. And this actually does end up working if you do it carefully enough. The problem is there's actually another polynomial, there's another guarantee that I haven't told you about, and that needs to be satisfied. It might actually be satisfied, but it's a lot easier to prove it for this one. And it was also the first one I thought of. So.
And also in the connection with the actual original quantum problem, is there any obvious reason why you only need x to approximate, or you only need the approximation on the interval 0, 1?
So yeah, again, I'm lying a lot of times, I guess. But so it turns out you don't actually need it. You need it for a little bit of a larger interval. You need it from negative beta log 1 over epsilon to beta log 1 over epsilon. I guess my understanding is that for small values, you want it to actually be you want it to be reasonable. But you don't necessarily for large values. Actually, okay, never mind. What I'm thinking doesn't actually make a lot of sense. I'll get back to you on this, but yeah, maybe I don't have a very good answer for this. Sorry.
Is the regime 1 over beta times log?
Sorry?
Is the regime of interest minus?
No,
1
it's
over
actually
beta?
negative beta. So it's beta is bigger than 1. So we actually want it to be true for an even larger interval. It turns out the construction I have works totally fine. I just did 0, 1 just to save on time a little bit.
Any other questions? Let's thank Sean. And the next speaker is Fran, who will talk about learning quantum circuits.
Hello? Oh, okay. All right. Thanks everyone for being here. So today I'm going to talk about learning shallow quantum circuits with many qubit gates. This is joint work with Robert Huang, who's now at Caltech. So in this work, we propose the first sample and time efficient algorithm for learning unitaries of shallow quantum circuits, specifically those with many qubit gates. And it turns out that this class of circuits has a name in quantum circuit complexity known as QAC0. I'll get into a definition of all of this, but I just want to start off by motivating why we should care about shallow quantum circuits in general and specifically their learning. So In particular, this class of shallow quantum circuits is actually the natural quantum analog of well-studied classes in classical circuit complexity, namely NC0 and AC0, for those who are familiar. And this result I'm presenting will be kind of a quantum analog of the well-known LMN result for these circuit classes. From a more quantum perspective, experimentally, we're currently in the noisy intermediate scale quantum era, in which noise kind of limits the circuit depth we can run. So really, in practice, all we can do today is running these shallow quantum circuits, and so it's important to be able to learn and characterize the circuits we can run today. From a theoretical perspective, shallow depth quantum circuits are of pretty large interest right now. It turns out that they can be more powerful than their classical counterparts. We believe their outputs are actually classically hard to simulate, and only recently has progress been made towards their learnability. So before I dive into all the learning stuff, I want to just spend a bit of time defining the two main circuit classes we'll be discussing in this work. So I'll start off with QNC. And whenever I add this little 0 after a circuit class, essentially all I'm saying is you're adding the constraint that it's going to be constant depth. And so QNC is the class that consists of arbitrary single qubit gates, and CZ or Toffoli gates, which are a special type of multi-qubit gate, which have the key constraint that they're also only constant width. QAC0 is a very similar class to QNC0. It's also constant depth. It also has arbitrary single qubit gates. And really the key difference is just that now you're given CZ or Toffoli gates of unbounded width. So these gates can act simultaneously on all the qubits in your system. Okay, so now I want to briefly motivate why we should care about these classes that have large many qubit gates. So prior to our work, there was actually quite a few gaps in the learning of the QAC0 circuit class. So in particular, Robert, my co-author, and many collaborators established efficient worst-case learning of QNC0. However, the approach relied very crucially on the fact that the gates they were using were, or the gates in QNC0 are constant width. I also had prior work focused on learning of QAC0, but in that work, we actually weren't able to learn a full description of the QAC0 circuit, just a single output channel. So just think of the circuit where you constrain to a single output qubit. And also, it had the really big drawback that while we achieved efficient sample complexity, the runtime was actually exponential. Okay, so from a more circuit complexity perspective, QAC0 is a pretty interesting class in that it actually lies immediately between QNC0 and QNC1, the class of logarithmic depth circuits of constant width gates. And I didn't mention this, but I guess the circuit classes that have actually finite width or constant width gates, those are the ones we can actually expect to implement in practice. So really, anything we can say about QAC0 is fundamentally making progress towards saying something about learning or understanding logarithmic depth circuits that we can actually implement in practice. And then the last key point I wanted to make is that it's a really big open question right now in quantum circuit complexity, whether QAC0 contains fan-out, which actually quantumly is equivalently to parity. But the really important consequence of this is that actually QAC0 with fan-out is a super powerful class. And it turns out that it can approximate really powerful computations like sorting, arithmetic, phase estimation, and even the quantum Fourier transform. So if you could implement fan-out in this constant depth class, you could actually run Shor's algorithm with a constant depth circuit, which is really powerful. All right, so now for the results of our paper. This is really our main theorem statement. So if you're given an unknown n-qubit depth d QAC0 circuit implementing some unknown unitary C, we show that we can actually learn a 2 n-qubit unitary, U, such that U is close to C tensor C dagger, so you also get the inverse circuit for free, according to an average case distance measure known as the average gate fidelity. And we're able to show that the procedure's sample and time complexity are quasi-polynomial, which is very efficient, and actually for those who are familiar with the LMN work, exactly matches the sample and time complexity of LMN for learning classical AC0. So one of the drawbacks that you might notice relative to the prior work on learning QNC0 is that our result is only with respect to an average case measure and not a worst case measure. And so in our paper, we actually construct an example of an explicit unitary implementable in QAC0, which if you wanted to learn it to a worst case measure, would actually require exponential samples. So really, average case learning is all we can expect to do efficiently. We also offer a procedure for doing efficient circuit synthesis from our learned unitaries, and really this was us trying to make progress towards a notion of proper learning. However, our efficient algorithm only achieves a quasi or a polylogarithmic depth QAC implementation, so we're still far off from proper learning, but you might expect proper learning to be hard to achieve since proper learning of AC0 is known to be pretty hard. And then finally, the main limitation or drawback of our result is that we actually are only able to achieve the sufficient learning for QAC0 circuits with a logarithmic number of ancilla. However, we do offer a conjecture in our paper, which, if proven true, would extend our results to polynomially many ancilla. And I just wanted to conclude the talk by kind of going through a high-level proof sketch of how we were able to show the sufficient learning. So really at the core of our argument and all the prior works is this notion of a light cone argument, which I'll explain. And this light cone argument is used both in the prior work by Robert and myself, both for sewing light cones into unitaries and then actually approximate learning of QAC0 light cones that our result then kind of combines and builds on top of. So to start off with the notion of a light cone, imagine I have a quantum circuit and it has many inputs and inputs. But then I am really just interested in a single output qubit. If I look back from that output qubit, in many cases, you'll see that there's only a subset of the actual input qubits which are going to directly connect to that output qubit. And so what we can do is delete kind of all of the gates that lie outside what we refer to as a light cone, and we'll see that we're only left with a subset of the original input qubits. Now for QNC0, which is constant depth and only has constant width gates, the size of this light cone is itself constant. However, for QAC0, where you have these gates that can simultaneously touch all of your qubits, what you find is that actually your total number of input qubits might not necessarily decrease, and using these sort of light cone arguments doesn't necessarily simplify things too much. All right, and so now I want to just kind of walk through the high-level idea of Robert's previous work on learning QNC0 unitaries. And really, what they showed is that if you have a QNC0 circuit and you decompose it into its light cones of all of its different output qubits, then it turns out that they can be efficiently sewed into a full unitary description of the circuit via a kind of tensor network formalism that looks like this. And you'll see that it gives you kind of C and C dagger, which is why we had that in our original theorem. And so really what this result is saying at a high level is that if you can efficiently learn the light cones, then that implies you can efficiently learn the full unitary. So great, you might think we're done here, but actually the key challenge in QAC0 is that, well, the light cones, they still act on all the qubits. So it's not necessarily much easier or more efficient to learn the light cones directly. And this is where some prior work by myself and others on showing Fourier concentration of QAC0 comes in. And in this prior work, we were able to show that QAC0 light cones are actually well approximated in average case distance by much smaller light cones, actually a quantum analog of a junta. The proof intuition for this is that actually if you remove the wide gates, it won't actually incur too much error. Like it'll drastically shrink the size of your light cone, make it a junta, but overall, the approximation error you incur is not too bad. So it turns out that these much smaller light cones are a good approximation of your true light cone. And so in this work, we kind of really put together these two ideas to get a much stronger learning algorithm for QAC0. So we in particular leverage the approximation technique of my prior work to propose a novel quasi-polynomial sample and time algorithm for learning approximate QAC0 light cones that only act on quasi-logarithmic or polylogarithmic qubits. And really the key bulk of the work was in proving all of the learning guarantees that go into showing that all of this approximation stuff kind of works out. But once you believe that's true, really the crucial step for actually avoiding these exponential runtimes that plagued the earlier work was showing that while the learned light cones are not necessarily unitary, since they only act on polylogarithmic qubits, we can perform a singular value decomposition and project efficiently onto the space of unitaries. And then in the end, we use Robert's light cone sewing procedure to efficiently sew these approximate light cone unitaries into a full approximate unitary description of the circuit. And so that's kind of the high level idea. We take these light cones, we approximate them, we sew them together, and then most of the work goes into proving the approximation and learning guarantees. So that's it for me. Thanks, everyone.
So you mentioned that Shor's algorithm is in QAC0 with fan-out. Are there any good examples of quantum algorithms which are not in QAC0 with fan-out?
Ooh. I wouldn't have a good answer to that off the top of my head. So QAC0 with fan-out is usually seen as an extremely powerful class, but actually the kind of key belief right now is that QAC0 does not contain fan-out unless you have exponentially many ancillas, or that's the big conjecture. So in practice, we shouldn't expect Shor's algorithm and all of these to actually be implementable in constant depth. But
I think you also mentioned your algorithm works for circuits with logarithmic ancilla. Is there a barrier to going to polylog ancilla, or?
Yeah, so it works for, I guess it does work for polylogarithmic ancilla. But the key reason we have that limitation is actually because the prior work on doing these light cone approximations fundamentally distinguishes between input and ancilla qubits. And really that approximation starts to break down or degrade when you have more ancillas. And crucially, it stops working once you get much past polylogarithmic ancilla. So we inherit that issue which plagued kind of the prior work and the prior learning algorithm already.
I may have missed this, but how are you provided access to the circuit? What is the learning model? Is it like query access, or is it like a random X you see the value?
Yeah, so in our work, we kind of use this classical shadow tomography. I don't know if you're familiar, where you're kind of able to query the circuit with random inputs and measure with respect to a random basis.